Mobile Automation Group, Online Training Program, Module 2. Technical Capabilities of Mobile Automated Vehicles, MAVs. Introduction. Welcome to Module 2. In this module, we're going to explore how the vehicles in a mobile automated vehicle system work. How did MAV safety and navigation technologies develop? How do the vehicles know where they are going? Will the vehicles operate safely in my facility? Will the vehicles be able to move the loads? How are the vehicles powered? How maneuverable are the vehicles? And what type of controls are on the vehicle? How did MAV safety and navigation technologies develop? First, let's look at how MAVs have gotten even safer over the years. This image shows the first known AGV guided O-matic by Barrett Electronics from 1953. Let's look at how safety and navigation technologies evolved over the last few decades. In the 1953s, we saw a fixed path emerge with wire guidance navigation, followed by mechanical safety bumpers. In the 1970s, we saw tape, magnetic or optical navigation. Then, in the 1980s, came the magnetic navigation via waypoints embedded in the floor. In the 1990s, still in fixed path, we saw inertial, magnetic, and gyroscopic navigation. And in virtual path, laser navigation via triangulation of fixed reflectors. Then, in the 2000s, came non-contact safety bumpers. And in 2010s, continuing the virtual path evolution, we had natural feature navigation and simultaneous localization and mapping, SLAM, navigation. And now, in the 2020s, the virtual path evolution gets into outdoor safety scanner. How do the vehicles know where they are going? MAVs use a variety of different navigation systems to travel safely. Let's break them down. Here are the typical localization systems used in MAVs: LiDAR, laser triangulation, natural feature or SLAM, inertial, magnetic tape, magnetic grid, wire, optical, and machine vision. Keep in mind that in certain applications, more than one form of localization may be used by a vehicle or sensor fusion. How do the vehicles know where they are going? Laser triangulation localization systems. Most mature method of MAV navigation. Reflective targets are mounted throughout the plant at known positions. A laser scanner is mounted on top of the vehicle. The laser scanner strobes plant for reflective targets. The vehicle control algorithms calculate the exact vehicle position via triangulation. Natural feature localization systems. Reference images of the operating area are recorded and stored in the vehicle's memory. Uniquely identifiable, naturally occurring features are identified in the operating area. Vehicle's actual position is calculated based on its relative position compared to those natural features. A camera or LiDAR can be used to record features during setup and sense features during navigation. LiDAR can be a separate sensor or the same sensor that is used for the safety system. Inertial localization or navigation systems. Reference points, often RFID tags or 2D barcodes, are embedded in the floor at certain XY coordinates in a map of the system. Reference points are detected by a sensor on the vehicle as it passes over the reference point. A gyroscope on the vehicle measures and maintains vehicle's heading. A wheel encoder on the vehicle calculates the distance traveled. Vehicle uses feedback from all three devices to determine location. Magnetic tape localization navigation systems. Tape is adhered on the surface of the floor. A sensor on underside of vehicle detects the magnetic tape. Can operate off tape path via dead reckoning. Similar to wire localization, that will be covered ahead. Grid localization systems. Reference points, magnets, or 2D/QR barcodes are embedded in the floor in a grid pattern. Reference points are given XY coordinates, which are stored in the vehicle's memory. The reference points are detected by an onboard sensing device. A gyroscope on the vehicle measures and maintains vehicle's heading. A wheel encoder on the vehicle calculates the distance traveled. Vehicle uses all three devices to determine location. Wire localization or navigation systems. Navigates using a continuous wire which is embedded in the floor. Antennas located on the vehicle detect signal from the wire. Uses encoders on wheels to calculate distance. Typically used in retrofits, system replacements, and expansions, as well as very narrow aisle, VNA automation of turret trucks. Optical navigation systems. Chemical or tape strip is fixed or painted to the floor. Vehicle has an onboard sensor which allows it to detect the path. Some systems use an ultraviolet UV light source under vehicle to illuminate the strip which may not be visible with non-UV lighting. Not typically used in plants or warehouses because floor line needs to be cleaned or reapplied. Mechanical bumpers. Uses a limit switch to stop operation of vehicle when the bumper contacts an obstacle. The detection field is typically a plastic, flexible metal or foam bumper material that will compress and collapse when contacting the obstacle and trip the limit switch. Has a fixed bumper size shape, and bumpers can require maintenance and replacement. Will push light objects such as waste materials out of the path of vehicle. Special applications still utilize this form of safety, however, state-of-the-art has advanced to laser systems. Laser safety system. Uses a 2D laser that scans the environment in the direction of travel a few inches above the ground. Design intended to recognize any human inside the travel path, either standing and unaware of the approaching vehicle or on the ground, for instance, unconscious. The detection field is typically dynamic and contains a warning, slow down zone and safety stop zone that adjusts with speed and curve angle. Additional sensor can be on the side of the vehicle for 3D coverage. Safety standard for guided industrial vehicles and automated functions of manned industrial vehicles. LANSI ITSDF B56.5-2005 provides guidelines regarding vehicle safety. An American national standard. International Truck Standards Development Foundation. The complete standard can be downloaded at www.itsdf.org. Will the vehicles be able to move the loads? Truck MAVs. Able to interface with the floor, block stacking, racking, stands, and conveyors. Resemble typical manual fork truck models, counterbalance, reach, outrigger, forkover, etc. Can be fitted with typical manual fork truck load handling attachments, forked, clamp, single, double, etc. Conveyor and platform MAVs. Very compact design with vehicle typically directly under the load. Able to interface with stands and conveyors. Load handling typically via conveyor or lift on the top of the vehicle. Can have no load handling ability if loaded or unloaded by external means, like crane, etc. Tugger MAVs. Tug several, typically up to 3, wheeled carts. Loads must be placed on and removed from carts manually or with other automated machinery. Provides most economical solution, fewer vehicles than MAV solutions that only carry one load per trip. Person-to-goods MAVs. The person, also referred to as the picker, and the MAV navigate to the goods for order picking. Most often, the MAV will not carry only one order, but will work with the picker to gather items for multiple orders until the load capacity is exhausted. The full MAV leaves and is replaced by a new empty MAV, allowing the person to continue work. Instructions to the person can be given via a GUI on the MAV or via handheld or voice-directed device worn by the picker. Case-to-person MAVs. Case-to-person MAVs typically have a mast that an inserter/extractor moves up and down. They extract cases from shelving and deliver to a goods-to-person station. In some cases, these larger robots hand off to small, faster MAVs that enables the larger MAV to stay in aisle. Sortation MAVs. Sortation refers to rearranging items in a new order, mostly to accommodate individual orders. Sortation MAVs are typically loaded after warehouse picking processes are complete. They then discharge their load to a consolidation area where individual orders are built. Sortation processes in e-commerce are frequently high-speed applications requiring high-speed MAVs. How are the vehicles powered? Most MAVs are designed with integrated onboard rechargeable batteries to power their operation. Power source. Most vehicles are powered by rechargeable batteries that are swapped out when depleted, opportunity charged at a charging station during slow periods, wirelessly charged, or connected to charging shoes at a workstation. Battery types include lithium-ion, lead-acid, thin-plate pure lead TPPL, NiCad, lithium iron phosphate LFP, and sealed. Some MAVs are powered by fuel cells. How maneuverable are the vehicles? MAV drives can be configured in multiple ways. Drive configuration is defined by the arrangement of wheels on the vehicle and by which wheels are driven and have steering. Determines the maneuverability of the vehicle. Also affects the vehicle complexity and cost. Common types include tricycle, differential, and quad. Other types can be used for unique applications requiring high capacity, limited wheel or floor loading, and other environmental conditions. Let's look at the most common drive configurations. Tricycle drive, most common on AGVs. Provides precise vehicle tracking. Degree of maneuverability acceptable for most applications. Differential drive. Steers using differential speed and direction of drive wheels. Maneuverable. Can rotate around the center of the vehicle. Common on older unit load vehicles. Vehicle angular positioning less precise. Quad drive. 2 steer and drive motors. Maneuverable, can rotate around the center of the vehicle and move sideways. More complex than other drive configurations. What types of controls are on the vehicles? MAVs are equipped with multiple controllers and sensors. Vehicle controller, PC-based or other controller in the vehicle that includes processor and I/O to provide navigation, communication, and operation of the vehicle. Manual controls allows manual operation of the vehicle. Maintenance and operator interface provides calibration, troubleshooting, and verification of vehicle parameters. Motor, AC or DC, motors that provide steering and XY vehicle movement. Motor controller, AC or DC, provides the control signal to the motors for vehicle movement. Here are some other controls and sensors used on MAVs. Navigation controls provide real-time feedback on actual vehicle position for navigation of the vehicle in the facility. Load position verification sensors, sensors mounted to the load handling attachment to make sure that the load is positioned correctly during vehicle operation. Interface handshake sensors, sensors mounted on the vehicle and interface equipment that provide a communication link to ensure smooth load transfer between the two. Obstacle detection sensors, sensors on the vehicle which bring the vehicle to a safe stop before contacting any obstacle that it may encounter in its path. Congratulations! You've finished the second training module. Here are the upcoming online training modules on mobile automation vehicles. Module 3, how do MAVs fit in a system? Components that enable systems. Communication methods. Mapping and configuration software. Fleet management software. System interface options to ERP or WMS. Human and machine interface HMI. Battery charging methods. And common traffic rules and considerations. Module 4, MAV applications. Typical and ideal applications, common processes targeted, and key industries utilizing them. Module 5, typical justifications for MAV investments, labor concerns addressed, safety and ergonomics improvements, operational efficiency gains, risk mitigation and future-proofing through flexibility, and indirect cost reduction. Module 6, a common approach to MAV adoption, common steps involved in starting a project. Key information to collect. Simplified calculations of fleet required. Considerations for simulation. And common calculations used for justification. For more information, contact MHI's Mobile Automation Group at mhi.org/mag.